Assalamualaikum warahmatullahi wabarakatuh. It is pleasure to be here today. Managing raw material inventory is one of the most critical challenges for micro, small, and medium enterprises. In today, unpredictable market. Today, we will presenting our research that title is a dynamic system approach to analyzing raw material inventory dynamics in a Muda Mudi Jaya Lumpur MSME using software VENSIM. So before we start our presentation, let us introduce ourselves. For me, Ihsan Hidayatulloh, that number 24032010132.
My name is Niko Rensa Putra. My number is 24 and 126.
My name is Sava Andhika Wiryamanta at the number 240320100127. Next. Introduction. In this study, we focus on Muda Mudi Jaya, a local culinary business that produces traditional Indonesian Kuala Lumpur. The company daily production highly depend on the availability of raw material including wheat flour, sugar, egg, and coconut milk. However, this research specifically focused on wheat flour because it represented approximately 60% of the total raw material requirement and play a critical role in the production process. Currently, the business faces several challenges, such as fluctuating market demand, delay in raw material procurement, and limit warehouse capacity. This issue can lead to inventory imbalance and disrupt the production process. Therefore, this study aims to analyze how factors such as market demand, purchasing budget, warehouse capacity, order rate, and lead time affect raw material availability. To address this issue, a system dynamic approach using VENSIM is employed to model inventory behavior and support better inventory management in the future. Based on this issue, this study addresses three main research questions regarding the factor affecting inventory, development of a fancy model, and the use of simulation result to maintain inventory stability. Next. Literature review. This study adopts a system dynamic approach based on a previous reference study. The research was conducted using secondary data and model using VENSIM software. The process includes developing the causal loop diagram, verifying and validating the model, and simulating for policy scenario. Based on the simulation result, the increasing raw material scenario was selected as the most suitable policy. For data analysis, three main tools were used. First, system dynamic was applied to analyze how inventory variable change over time. Second, the causal loop diagram was used to identify cause and effect relationship among variables. Third, the stock flow diagram was developed to quantitatively represent the inventory system. The theoretical foundation of this research include concept of system and simulation, modeling, demand and supply, MSMES, verification and validation, and the use of VENSIM as a tool for system modeling and simulation. Next. Problem analysis. This diagram shows that wait for supply in uncertainty is influenced by six main sectors: supplier, inventory management, production, market demand, and finance, as well as warehouse and material quality. Change in one sector can affect the other. Therefore, a system dynamic approach is needed to understand this interacts and support better inventory decision making. Next. Nah, this is Bone diagram show the root cause of wheat flour supply uncertainty. The cause are categorized into six factors: method, man, material, machine, environment, and money. Key issue include effective inventory management, forecasting forecasting error, supplier and harvest uncertainty, limit production capacity, environmental factor, and financial constraint. These factors collectively affect the stability of raw material availability. And then, after identifying the root cause through the fishbone analysis, the next step is to examine the relationship among these variables using a causal loop diagram. Next.
So the next our the next our material is conceptual model. Next. This is our causal loop diagram. And the next. And this is our soak and flow diagram. Why we use two diagrams for our system? Because we should to make architecture of dynamic system that make our modeling in reality system. So the first is causal loop diagram for mapping intersystem interaction. Using causal diagram is connecting the agricultural sector or upstream and inventory management, internal and production operation, warehouse quality, and business finance. So the main mechanism is three types, and the first is balancing loop. Automatically regulates raw material procurement based on warehouse stock level to prevent stockouts. And the second is open linear flow. The influence of external factors like weather and land productivity on floor availability in the market. And the third or the last is quality depreciation, a direct relationship between room temperature and storage duration on the accumulation of spoiled raw material. So the three mechanism is help us to see the intersystem interaction. And the next is stock and flow diagram. So there are two aspects. The first is stock component, and in the stock component there are two stock. The first is raw material availability, and the second is business capital. And the first stock is tells about floor inventory increases through inflows, purchases, and decrease through outflow like production and damage or wastage. And the second or the last is business capital. It tells about capital liquidity increases through sales revenue and decreases through total operating expenses. And the next is auxiliary variable. There are lead time, kebijakan pembelian, estimasi kebutuhan, and faktor konversi tepung. And the next is stochastic approaches and policy optimization. There are three aspects on stochastic approaches and policy optimization. And the first is uncertainty modeling. It tells about integrates random uniform function for weather factors and customer demand to simulate real-world stochastic volatility. And the second is scenario planning. Uses the model as a framework to test various intervention scenario to prevent liquidity deficits. And the last is strategic objective. It tells about achieving market demand satisfaction through the synchronization of production capacity and consumer preference. And the last is mathematical formulation and simulation model. Why we use two mathematical formulation? Because to have a validity of the real system. There are three aspects on this subpart. Especially the first is like equation rigidity. It tells about transform qualitative causalities into process differential and algebraic equation. Example like using inter function for stock and if then else for procurement policies. And the second is model validity to ensure every parameter such as lead time, text, and cost adheres to conversation laws to guarantee simulation accuracy. And the last is analytical tooling. It tells about utilize VENSIM software to transform the model into an instrument capable of predicting future system behavior. So the next is I will tell about verification and validation. This process we should to do because we want the model is the same as a reality. So we should to do this process. So the first, I will tell about model verification analysis. There are two verification method that we use. The first is model verification, and the second is on unit verification. The first is model verification or structural verification. It performs comprehensive testing of the stock and flow diagram to ensure the absence of logical errors and syntax mistakes. So, verified by VENSIM model is OK status message confirming that all causal links, mathematical formulation, and feedback loops are integrated and complete. And the last is confirmed that the model is technically valid from a computational standpoint with no broken logical loops. And the second method is unit verification or unit consistency check. It's conducted a dimensional analysis on all mathematical equations within the model. It confirmed by the VENSIM unit are OK status message, indicating that all variables, parameters, flow rates, and stock components are dimensionally consistent. And the last is ensure that there are no contradiction in measurement units across interconnected variables, validating the model scientific dimensional integrity. And the next is model validation analysis. In here, we use MAPE for our model validation. Why we use that? This model accuracy was assessed by comparing actual raw material availability data against simulation output from 2022 to 2025. The mean absolute percentage error or mapping method was employed to quantify the deviation between the simulated model and the real-world field data. So, the initial calibration, the smallest absolute error was recorded in 2022 at 0%, confirming that the model initial conditions are perfectly calibrated with the actual data. And the highest deviation occurred in 2025 with an error rate of 1.1360 or 63 or 13.60%. This variance is attributed to stochastic dynamics within the actual system that are not yet fully captured by the model parameters. And the average absolute error across the entire simulation period is 0.0530, resulting in a final aggregate mapping of 5.30%. So, based on the standard forecasting accuracy criteria, a mapping value below the 10% threshold signifies that the model possesses highly accurate predictive capability. So, the stock and flow model is the clear, valid, and representative of dynamic behavior of raw material availability in the real world. So, in the conclusion, this model is valid. And the next is I will tell about sensitivity analysis. Why we use this process? Because we should to know interaction between other variables if we change the parameter of that one variables. Next. So we use three changes the parameter variables. The first one is raw material price, and the second one is harvest area sensitivity, and the third is production target. And the conclusion of this sensitivity analysis is the sensitivity analysis shows that increasing raw material price, production targets, and with harvest area all contribute to higher raw material availability within the system. However, supplier capacity through harvest area expansions has the most significant impact, creating substantial inventory fluctuation and highlighting the need for better inventory and storage capacity management. So, for the conclusion, there are three of variable very have a sensitive for our model.
Next, let's talk about result and analysis. Result analysis, dynamic system simulation results, problem analysis and system behavior, upstream constraint, weather uncertainty effect with productivity, surface area, 500 hectare area. Productivity 3,200 kilogram per hectare area per year. Internal warehouse constraint. Actual temperature 30 degrees Celsius. Ideal temperature 25 degrees Celsius. Higher spoilage and inventory degradation. Business impact raw material price 18,000 per kilogram. Initial capital 10 million. Critical purchasing limit 1.5 million. Inventory stability reduce business liquidity. Model verification and validation, structural verification, equation error detected, unit consistency successfully verified, material and financial flow structure are valid. Model validation, historical data period 2020 until 2025, average MAPE 5.30%. Error value below 10%, model categorized as very good forecasting model. Sensitivity analysis, raw material price scenario, price increase from 18,000 until 20,000 per kilogram. Inventory increase from this up to this. Higher prices trigger defensive purchasing behavior. Production target scenario, production target increase from this up until this unit per year. Inventory increase to 777.974 kilogram. Procurement intensified to support production expansion. Supplier harvest area scenario, harvest area increase from 500 until 2,000 hectare area. Inventory packet at this. Excess stock cues severe fluctuation and spoilage. Key takeaways, the module successfully passed verification and validation test. Inventory behavior is highly sensitive to policy change. Supplier capacity has the strongest impact on inventory stability. Integrated inventory management is required to prevent overstock and storage. Outline now. Let's talk about conclusion and suggestion. Implementation of software VENSIM aspect and before improvement and after VENSIM implementation, inventory planning, manual estimation, simulation-based planning, stock monitoring, difficult to monitor real-time stock evaluation, demand analysis, limited prediction, demand forecasting available, decision-making based on experience, data-driven decision, stock availability, risk of shortage, better stock control. Model accuracy no validation tool, MAPE 5.30%. Suggestion for implementation software VENSIM, improve inventory planning, regularly update simulation data, adjust order based on forecast, optimize warehouse management, control storage condition, minimize raw material damage, strength supplier management, build long-term supplier partnership, monitor lead time performance.
So, thank you for giving attention for our presentation. I'm very, very sorry if I have mistake on presenting our word or others. Thank you. Wassalamualaikum warahmatullahi wabarakatuh.